Griffiths E&M section 5.2.2, example 5.5. We have mentioned that we can go ahead and use the Biot-Savart law to calculate the magnetic field from a steady current. That Biot-Savart law looks like this. Over r squared. So let's go ahead and test it. So I have an infinite wire, or at least a very long wire, carrying the current I to the right. I'm going to put my coordinate origin there, and we'll say that this current is moving in the z hat direction. Okay, so that's the z is to the right here. I want to know what is the magnetic field at a point P, which is a distance s away from my wire. Okay. So I've picked an arbitrary point on my wire. That arbitrary point means that this is my r prime vector. Sure, we'll call that. That means that script r is this vector, and I'm going to want to evaluate dl prime. So I should figure out what exactly that is. That's the infinitesimal step I would make along my wire as I try to integrate to figure out what the magnetic field is. Okay, so this bit right here is dl prime. Some small step over there. Okay, so just like when we did Coulomb's law, we had to figure out what all the pieces were. We're going to go ahead and do this with a good amount of trig. So dl prime cross r hat. Okay. dl prime cross r hat. We're going to evaluate that like you might have learned about cross products at the very beginning of your time. There's the magnitudes times the sine of the angle between them. So this is going to be dl prime. This is going to be r hat. The magnitude of r hat, though, is just 1. Okay, and then times the sine of the angle between them. Okay, I'm going to go ahead and call this alpha. That's the angle between them. Times sine of alpha. And we'll call this other angle theta. And the sine of alpha, because alpha and theta are related to each other, is just cosine of theta times dl prime. Okay. I need a direction associated with that because I don't want just the magnitude. I'm going to go ahead and say that because the direction of my magnetic field is solely due to this, and I know that the right-hand rule, put your thumb along the current and curl your hand, means that at this point up here, the magnetic field is pointed towards me. I'm just going to keep it like this. Okay. So it's not super helpful because I don't know what dl prime is currently. Well, I know that l prime is the distance from my origin right here to L, or to the element that is, I don't need to erase that. It's the distance from, basically L prime and R prime are the same here. Okay. I have a distance L prime away from this origin point, and I increment dl prime. Okay. I can go ahead and write L prime as S times tan of theta, because this triangle right here. And I can take the derivative of both sides with respect to theta. Derivative of S, that's a constant, and then secant squared theta. also known as S over cosine squared theta. So then dl prime is S over cosine squared theta times d theta. We're just pulling the d theta over to the other side. And then I can rewrite this expression for dl prime across r hat, plugging in value for dl prime as, I'll write that whole thing, crossed r hat is equal to S over cos squared theta times cos theta d theta, pointing out, and that's equal to S over cos theta d theta, pointed out. Okay. I can also rewrite S using that same triangle that we have earlier as just script r cos theta. So then, therefore, 1 over script r squared is equal to cos squared theta over s squared. So I combine this bit with this bit in my Biot-Savart law, and I'm left with my magnetic field is equal to mu naught I over 4 pi integral of S over cos theta d theta times cos squared theta over s squared. With the direction out. I think I have all the right pieces here. All right, that looks good. Start canceling some things. Cos theta gets rid of one of those. One of those s's goes away. I'm left with my magnetic field is mu naught I over 4 pi cos theta d theta pointed out. Okay, now I need bounds on my integral. So I'm going to go ahead and say that we have an infinitely long wire. Right? If I have an infinitely long wire, that means that my wire begins, as I go further and further out here. Right? The furthest angle right here for theta is just going to be minus pi over 2. We'll go minus pi over 2 and also pi over 2 here. Integral of cosine is going to be sine. So mu naught I over 4 pi sine pi over 2 minus sine minus pi over 2 pointed in this direction. Sine of pi over 2 is 1 minus sine of minus over 2 is a minus 1 minus a minus 1. It's mu naught I over 2 pi pointed out. All right, I've carried this really clunky notation around to say that the magnetic field is pointed out at this point P that I cared about. But what if I were to evaluate the magnetic field at, let's say, a point here? Well, the magnetic field would be, using the right-handed rule, would be into the page, right? So actually, this clunky notation is only valid above my wire, and the robust solution that doesn't care about where I am on the wire would be to say that now my magnetic field, oh, I missed a 1 over s somewhere. I missed a 1 over s over here. Is no longer just some arbitrary direction, but it's going to be in the, well, since we defined the current to go in the z hat direction, this is also in the phi hat direction. All right. So my current flows in this direction, in the z hat direction. My magnetic field circles around that, and it gets weaker with 1 over the distance away from my wire. S.